today I will be talking about the AI-aided systematic numerical modeling of AMOC surface conditions using many deep learning architectures. So the main background of this work is to look at oceanic circulation, especially in the context of climate change and the increasing acceleration. Many models have predicted that the AMOC will eventually slow down and potentially even shut up completely in the future. The AMOC is a hugely influential system of heat transfer within the Earth's oceans, and it as such represents likely the largest factor in potentially figuring out how the increased CO2 concentrations in the atmosphere may affect AMOC features such as the speed of the Gulf Stream or the extent of undersea overflows in the Greenland region. So this work first aims to utilize AI to model primarily the surface conditions of the North Atlantic. And as a result, we can at least understand how the transport of heat is being conducted at the surface. And secondly, and no less significantly, it will help us figure out the extent to which AI can help with specific ocean modeling. So in this case, I specifically will talk about the transfer of heat. Oceanic and atmospheric fields are plentiful in the ocean, but however, it's a very complex system. Many of these features not only have we not measured until relatively recently, but our historical data is also rather questionable at times. That being said, this is a system that includes a lot of different factors, and this is the prime motivation for using an AI model, which can deal with relatively correlated systems. And with the amount of potential data that you could utilize here, it's something that is very promising, and you can seek to model this complex system as such. Our work here is to accurately model these fields. So the data set we utilized is the ICARS data set from UCAR. The data goes as far back as 1800, but prior to the 1900s, there's just not as much quality data, and it's increasingly unreliable. So for the model training, we only use data from 1900 to 2014, and we validated on 2015 to 2024. The temporal resolution is monthly, and there are two spatial resolutions. The 1x1 was obviously higher resolution, but unfortunately the data is relatively limited and it only goes as far back as around the 1960s. In contrast, the 2x2 data goes as farther back. The features that are included in the data set include these. While there are other derived variables that are present within this data set, we want to start from our most basic key features, so to speak, and so as a result, we do not specifically go beyond these 9. And importantly, the only one of these which is not observed is specific humidity, which for moisture purposes we found to assist our model greatly. So the goal here is to model one of these oceanic atmospheric fields from the other 8. And we implemented 3 different models to perform this task. The first was the regular convolutional neural network. The second was the convolutional long short-term network. And the third is the spatiotemporal transformer. Now, before we discuss how these models work, it's good to have a primer on what we mean when we say we're training a model. So the steps of a machine learning model, you split the data into training versus testing and features versus targets. So in our case, our training data is from 1900 to 2014. Our testing is from 2015 to 2024. Features would be the 8 atmospheric fields that we are providing into the model, and the targets are the one that we are pulling out. We feed the training features into each sequential layer of the model. We compare the final output against the training targets. Then we perform backpropagation. We look at the loss function and we say, okay, well, we have the mean squared error, for example, and we want to reduce that as much as possible. That's our loss function. We perform backpropagation on previous layers. We repeat steps 2 through 4 for multiple epochs. And after some time, once you've reached your hopefully your local minimum, you will end your training and you validate on the testing. So the first model we used was the more important strategy here is that it's based on image processing and just general analysis of you have a matrix of values that you wish to predict, and from the inputted data you have kernels to perform convolutions on top of it, and you have few of these layers together, and you'll end up with spatial association through the highlighting of certain terms, certain features. The second one would be the convolutional long short-term network. Now, a regular LSTM model involves the persistence of memory. Certain features will persist longer depending on temporal proximity. Unlike the convolutional LSTM models in general themselves do not have this ability to connect, to associate across time, because because by itself, or rather, correction, there is not enough spatial association because it is pure dense networks. This convolutional long short-term memory network allows you to do spatial and temporal associations. Our third model is provided by Dehim et al., and it is a spatiotemporal transformer. Now, unlike large language model transformers, these actually rely on data and not tokens of words, but tokens of different vectors in your data, so to speak. These tend to be more computationally intensive, but the advantage is that they have the potential to do rolling predictions into the future with regard, whereas the other two previous models, they are limited by the features. And so if they do not have the data for the features, then they cannot predict the targets. Now, there are many different hyperparameters that you can adjust, so to speak, but for the most part, the architecture is what really counts. When we perform sort of analyses, what we are really trying to do is for one of these variables, we want to find the lowest loss. But as you can see here, the distinguishing feature is not as much compared to when you actually choose different architectures. This is one of the limitations to utilizing AM models for this sort of work. So before we start talking about the models, it's good to know where simple linear regression stands, simply as a baseline from where we compare. The brackets T means the global mean temperature, and over the North Atlantic region, and for over different temporal rolling averages, we have these various linear regression values. And in the Gulf of Maine, we have slightly lower ones. And it's worth noting that the grid looks something like this. As you can see, it's rather messy, and it's very difficult to predict anything out of this. And for those interested, that is the Gulf of Maine region. Okay, more closely, if we can analyze linear regression between one of the features in the data set itself, for example, air temperature directly against sea surface temperature, and all 8 fields, so doing a 8 predictors to predict mean sea surface temperature. And in the left-hand case, you can see the root mean squared error is about 2.45 degrees Celsius, and in the right-hand graph, we see it is about 1.75 degrees Celsius. So those are the RMSE values with which we will judge our models. So first we have the convolutional neural network results. Our root mean squared error is about 0.946 with the associated loss. And in terms of looking at the errors in the monthly SST, so in this case, we can predict sea surface temperature. We see that there is slight seasonal oscillations, and this graph isn't shown necessarily here, but we found that on average, in the northern latitudes, the error oscillations tend to be greater at the seasonal extremes. So during the summer, your magnitude of error in the sea surface temperature in around, say, the Arctic regions would be greater than it would be at the equator. And this would be the case in the summer. It would underpredict, and in the winter it would overpredict, but it would overpredict by less. For the convolutional LSTM, we had a similar but slightly lower value of 0.927 degrees Celsius. I have an associated contour map there. And we see a similar behavior in the convolutional LSTM, but in this case we can see there's a slight upward trend in the mean squared error as time goes on. And in the third case we have our SDT results. Now these do not this model did not work out as well, likely due to the complex behavior, amount, incredibly heavy computational tasks required to run this model. And we are not just limited in sea surface temperature. We can predict all the other 8 variables from just if you take one at a time, and you can use the other 8 to predict that one. And we have predicted most of them to satisfactory levels here. It's worth noting that in all cases, the errors tend to be exacerbated at seasonal extremes. And for example, you would expect air temperature to follow the sea surface temperature trends, which they do. And in terms of wind speed, for example, they would be the error would also follow similar trends, though it's not as extreme as you see in temperature. So in summary, we have trained 3 different AI models on oceanic mean sea surface temperature. We have the CNN, convolutional LSTM, and the SDT, and we found that out of these 3 models, the convolutional LSTM tends to work the best. Now, in general, we see that the error trends increase in magnitude, and we have northward migration of contour lines, and this suggests that warming is exceeding our predictions. If you assume that your model is going to predict the error points into the future, you will find that it tends to change. It will always underpredict the amount at which it is changing. These findings suggest this is a potential beginning of a new area where we have increased exponential change. And as a result, with properly cleaned and high quality data, AI modeling could quickly reach a decent accuracy against the real world data, provided that we provide enough data and, so to speak, into our models. So this is just the beginning. AI modeling is still a relatively new field, and we have chat-based predictions now, but this is nowhere near the same thing. And so we need to definitely consider more. We're not going to just throw all our data at a model and expect it to be able to perform satisfactorily. We will need to have specifically ocean-oriented models and architectures in order to be able to predict this, data that is not discrete and data that is not necessarily known all the time. When in the case of an image, you know exactly what each pixel is going to be, but for the ocean, you don't know. For more efficient use of greater computational resources is rather important. At the current pace right now, we have the computational resources, but we need to make sure that we are making our models utilize them to the greatest potential, to the greatest caliber. And in addition, our data is rather lacking. The ICARS data set not only has a lot of holes, but is in general rather limited in its historical span. And we hope to extend this to prediction of other oceanic features, such as ocean currents and importantly, salinity as well. Hopefully, we can add a depth analysis into the future and make this model 3D as opposed to just a surface. And most importantly, it's important to be integrated with physics models. And now we have shown that it will improve your RMSE by at least a factor of 2. We have to see what else it can do and whether or not we can predict into the future. These are the references, and special thanks to these professors.
Thank you very much. There was another question. We'll take it and then we can move on. Xavier?
Good morning, Xavier here. Firstly, great work. I think that you're asking the right questions and looking at why there are gaps with regard to state of the art and the things that we should be looking at as well on what we've been doing so far. So that's a good direction. Congrats for that and the thoroughness. But also at the same time, I can say that you can be looking at data and looking at what sort of model works and gives us models to think or results to think about and kind of describe what we're seeing, and therefore every sort of relation you can get out of this process, iterative, very difficult process nonetheless, is very limited to the quality of data you get.
Exactly.
Right. So going forth, then you raise very pertinent questions with regard to okay, now here we are, what now? And what I'm thinking is, isn't it more relevant to pay more attention to the freshness of data, and instead of discrete data, having a more continuous data feeds, because there are platforms, and you've got currently projects here, EU funded and everything, that aim at establishing scaffolding platforms, and you've also got other data providers, MLNet, Copernicus, and so on, that give 50 shades of different data, right?
Yes.
That we can work on, right? And what do you think of using going into the future? And I don't know if you consider these as research or approach direction on shifting your approach from a time frozen data set into something that is actually more usable going forth.
Yeah, that's a good question. Actually, I'm frankly very glad you brought this up, because from where I am in the United States right now, it's no surprise, recent challenges we face, but also in general, NOAA tends to not have very up-to-date data. One thing I was impressed by in coming to France and seeing the work that Copernicus and other data systems is, it's not only very they're complete, so to speak, but it's also provided in a data format that's very readily accessed. I didn't think I mentioned this, but I was working with Fortran. It's 2025. We're still working with Fortran here. Yeah, I would argue that the current historical, so AI models tend to have a great advantage if you have a ton of data. Currently speaking, this means you not only need to have a large historical extent, but also very good temporal resolution, but also strong historical extent. So I could not find much data from prior to the 1980s, prior to 1970s, before remote sensing came along, where you are able to do this sort of thing. In fact, for most cases, the climate models that we use, they're all simulated models. In order to create, let's say you have your climate at a certain time, and then you add some forcing, you see what the result is. That's what most people are working on nowadays. But I felt it was very important to connect it back to the real world data. Now, I would love to see greater quality control in terms of the data that we currently have. But I hope this is able to do this connection and between the simulated and the real world, and I hope that people follow this direction more in the future. So thank you for the question.
Thank you very much.